A supernova is the explosive death of a star. In just a few seconds, it releases more energy than the sun will produce across its entire lifetime. To understand why this happens, you need to understand a simple, constant conflict that exists inside every star. Gravity is always pulling the star's matter inward, trying to crush it into a smaller and smaller point. At the same time, the energy released by fusion, the process of atoms fusing together at the star's core, pushes outward with enough force to resist that crush. For most of a star's life, these two forces are in balance. A supernova happens when that balance finally, permanently breaks, and gravity wins. This matters to you because of what gets left behind. Almost every heavy element you interact with every day, the iron in a wrench, the calcium in your bones, the silver inside your phone, was created inside a star and scattered into space by an explosion like this. Without supernovas, the universe would still be mostly hydrogen and helium. There would be no metal, no rock, no planets like Earth. Understanding this process is understanding where the raw material of your physical world actually came from. Now let's build this up piece by piece, starting with how a star stays stable in the first place. A star exists in a state called hydrostatic equilibrium. This is the technical name for the balance between gravity pulling inward and the outward pressure produced by fusion at the core. This balance matters because without it, a star would either collapse in on itself immediately or blow itself apart immediately. Neither happens because the two forces cancel each other out. Think of a pressure tank in a building, the kind used to hold water at consistent pressure for a plumbing system. As long as the pressure inside matches what the tank is built to hold, everything stays stable. If that pressure ever drops or spikes without correction, the system fails. A star works the same way for millions or billions of years, until something changes the balance. In simple terms, a star stays whole because its own explosive energy is constantly pushing back against its own gravity. That outward push comes from fusion, and fusion runs on fuel. A star starts by fusing hydrogen into helium. This is the easiest, most efficient reaction available, and it's what a star spends most of its life doing. But hydrogen is a finite resource. As it runs low, the star starts fusing helium into carbon. When that runs low, it moves to heavier elements still, working its way up the periodic table. This matters because each new fuel produces less energy and burns faster than the one before it. A useful comparison is a construction crew working through a stockpile of materials. They use the cheapest, easiest material first. Once that runs out, they move to something more expensive and harder to work with. Eventually, they reach a point where there's nothing left to switch to. A star follows the exact same pattern, and it eventually reaches the exact same dead end. That dead end is iron. Fusing elements lighter than iron releases energy, which is what keeps the star pushing outward. But fusing iron does the opposite. It actually consumes energy instead of producing it. This matters because it means iron fusion cannot power the star. Once a star's core becomes iron, there is no next fuel to switch to, and no reaction left that produces outward pressure. Imagine a business that starts burning through its cash reserves just to stay open, spending money with no revenue coming back in return. That's what fusing iron is like for a star. It's an unsustainable move that only speeds up the end instead of preventing it. In plain terms, iron is the point where a star runs out of ways to hold itself up. This is the important part. Once the core is iron and fusion stops producing outward pressure, gravity takes over completely, and the results are immediate. The core collapses. With nothing left to resist gravity, the star's core caves in on itself in a fraction of a second, a process called core collapse. This matters because of how sudden it is. This isn't a gradual weakening over years, it's total structural failure almost instantly. A structural support beam that finally gives way isn't a slow bend, it's a sudden break, and everything above it comes down at once. A star's core collapses in the same abrupt way, going from stable to collapsed before anything can adjust or slow it down. Simply put, once support disappears, collapse doesn't take time, it happens immediately. That collapse doesn't stop quietly. As the core crushes inward, it reaches a point where it can't compress any further, and it rebounds, sending a shockwave outward through the rest of the star. This is the core bounce, and that shockwave is what blows the outer layers of the star apart in the visible explosion we call a supernova. This matters because it explains where the explosion's force actually comes from. It's not a fire, it's a rebound. An airbag works on a similar principle, a sudden compression event that instantly redirects force outward with enormous power. The star's shockwave does the same thing on a much larger scale, tearing the star apart from the inside out. In one sentence, the explosion you see is the result of the core hitting its limit and rebounding outward. What happens to what's left depends entirely on how much mass remains behind. If the leftover core is within a certain range, it compresses into a neutron star, an object made almost entirely of neutrons, packed so tightly that a teaspoon of it would weigh billions of tons. This matters because it shows just how extreme the compression really is. Picture a car being compacted in a junkyard crusher down to a fraction of its original size, but somehow keeping almost all of its original mass. That's the basic idea behind a neutron star, except taken to an extreme far beyond anything a machine could do. Put simply, a neutron star is what's left when a stellar core gets crushed down but not completely destroyed. If the leftover core mass is too great, though, the collapse doesn't stop at a neutron star. It keeps going, compressing further and further until it forms a black hole, a region where gravity is so strong that nothing, not even light, can escape it. This matters because it shows that not every collapse ends the same way. The outcome depends on mass. Picture a home's foundation sinking under a load it was never built to support, sinking further and further with nothing underneath to stop it. A black hole is what happens when that sinking never finds a floor. In plain language, a black hole is what forms when there's too much leftover mass for the collapse to ever stabilize. Not every supernova starts the same way either. What we've described so far, a massive star running out of fuel and collapsing under its own weight, is called a Type II supernova. But there's a second kind, called a Type Ia supernova, and it starts completely differently. It happens when a white dwarf, the small, dense remains of a lower mass star, pulls extra mass from a nearby companion star until it becomes unstable and detonates. This matters because the two types have different causes, even though both end in an explosion. Think of two different causes behind an engine fire. One comes from an overloaded fuel system being fed from an outside source. The other comes from an internal mechanical failure with no outside cause at all. Both result in fire, but the origin is completely different, and the same is true for these two supernova types. One of the most important results of all this is where new elements come from. Extreme heat and pressure inside a supernova actually create heavy elements like gold, iodine, and uranium that didn't exist inside the star beforehand. This process is called nucleosynthesis. This matters because it means these elements aren't simply released from the star, they're manufactured by the explosion itself. It works something like a manufacturing process that can only produce certain alloys under extreme heat and pressure conditions that don't exist anywhere else. Those materials don't exist until that extreme process creates them. Stated simply, some of the heaviest elements in the universe are created in the same instant that a star dies. Finally, all of this leaves something behind. The explosion's outer material spreads outward into space as an expanding cloud called a supernova remnant. This matters because that material doesn't just disappear, it becomes the raw ingredients for future stars, planets, and everything on them. It's similar to demolition debris scattered across a site after a building comes down, material that later gets reused to construct something new nearby. A supernova remnant works the same way on a cosmic scale. In one sentence, a supernova remnant is the leftover material that goes on to build the next generation of stars and planets. Let me show you exactly how this works by following one star from start to finish. Picture a massive star that has existed in stable hydrostatic equilibrium for millions of years, quietly fusing hydrogen into helium, gravity, and outward pressure perfectly balanced. As its hydrogen runs low, it climbs the fusion fuel ladder, fusing helium, then carbon, then progressively heavier elements, each stage burning hotter and faster than the one before it. Eventually it reaches the iron wall. Fusion can no longer produce outward pressure, and there's no next fuel to switch to. With nothing left to resist gravity, the core collapses in a fraction of a second, then rebounds, sending a shockwave through the star that blows it apart in the visible explosion. What's left behind becomes either a neutron star or a black hole, depending entirely on how much mass remains in the core. That single sequence, balance, fuel, collapse, explosion, remnant, is the entire life and death of a massive star, playing out as one continuous mechanical process rather than a list of separate facts. Here's what people most often get wrong about this topic. Many people assume an explosion this violent must be sudden and unrelated to anything that came before it, but it isn't. It's the direct result of the star running out of fuel over millions of years. It's easy to make this mistake because the explosion itself only lasts seconds, so it feels disconnected from everything that led up to it. The fix is to remember that the explosion is the final step of a very long process, not a random event. Another common mistake is assuming every star eventually goes supernova. It doesn't. Only stars above a certain mass threshold end this way. Smaller stars, including our own Sun, follow a much quieter path and never reach the conditions needed for this kind of collapse. This mistake happens because supernovas get so much attention that people assume they're the standard outcome for every star, when they're actually the exception. People also frequently treat neutron stars and black holes as interchangeable outcomes of the same event. They aren't. The difference comes down entirely to how much mass is left in the core after the explosion. This is easy to confuse because both form from the same starting process, so it seems like they should be the same result. The fix is to always tie the outcome back to leftover core mass, not to the explosion itself. Some people also assume that heavy elements like gold and uranium existed inside the star all along and were simply scattered by the explosion. In reality, some of these elements are created during the explosion itself, through nucleosynthesis. This confusion happens because it's intuitive to think an explosion just releases what was already there, rather than actively producing new material. Finally, people often treat Type 1 and Type 2 supernovas as the same phenomenon just because both are called supernovas. They come from entirely different starting conditions, one from a white dwarf pulling mass from a companion star, the other from a massive star collapsing under its own weight. This is easy to mix up because the visible result, a bright explosion, looks similar from a distance, even though the causes are completely different. This understanding has real, practical value. Because nucleosynthesis only happens under the extreme conditions of a supernova, elements like gold and uranium are naturally rare, which is directly tied to why they're expensive and difficult to mine. Because Type 1a supernovas explode with a predictable, consistent brightness, astronomers use them as reliable markers to measure distances across the universe. Without recognizing this, it's hard to understand how scientists calculate the scale and age of the universe at all. Knowing the mass threshold required for a supernova also clarifies that the sun will never explode this way, which removes a misconception many people carry from movies and pop culture. And understanding supernova remnants explains why our own solar system, including Earth itself, contains heavy elements in the first place, tying your own physical surroundings directly back to a star that exploded long before the sun ever formed. You can now explain why a star explodes instead of simply fading away, and tie that explosion directly to fuel running out rather than to random chance. You can now tell the difference between a neutron star and a black hole based on leftover core mass, instead of treating them as the same kind of leftover object. You can now identify two distinct causes behind different types of supernovas, instead of lumping every explosion into one category. And you can now connect ordinary objects around you and even your own body directly to a specific process that happened inside a dying star. This is the understanding you should have been given the first time you heard the word supernova, and now you have it.